And I'm showing something different here. I'm going into the research of the natural free-flying objects in space, the comets, which are not bound to their planetary periodic limitations and bring surprises to us. And because I'm working not in spaceflight, but at a company specialized on Java VMs, high-performance Java VMs for large heap sizes and low latency. But in my spare time, I'm providing a free website, providing daily Mars rover images, and I'm also researching independently into comets. And the opportunity was there in 2014 with a close encounter of Comet Siding Spring, reaching near 140,000 kilometers near Mars, and that was a good combination to combine both. And it provided some surprises, because the expectation of this relatively small comet back then was that with its low absolute magnitude of only 8 absolute, so really dark, that it doesn't have a large natural impact on the planet. Sure, spacecrafts need to take care. That was then avoided by maybe adjusting the orbits a bit of the existing Mars satellites. But the topic is here the natural impact on the planet. And that was expected quite low, with only maybe producing meteor shower, depositing material in the range of several hundred of kilograms onto the whole Martian upper atmosphere. But in the end, it turned out that this small object provided precipitation of 80 tons of metal, mostly magnesium, iron, sodium, into the upper atmosphere. And those 80 tons were measured results by MAVEN and MRO spacecraft, ultraviolet spectrography, and radar. Those were actually measurements in the upper atmosphere. The question is now, when the expectation was to see a few hundred kilograms, how can those 80 tons arrive there with this relatively low activity of this small comet? Because this huge amount, 1,000-fold more, would mean that the existing model of the ice ball comet would be too constrained to achieve that. And the second question was at first how to, or which trajectory is needed by individual comet tail particles to reach the atmosphere actually. Can it reach, or at which time do those objects need to be ejected from the cometary nucleus surface to achieve a sufficient trajectory to reach near or onto the planet even? And that was the purpose, to check that out with FreeFlyer. And the methodology I used here was simulate the particle tail under gravity and solar pressure for individual tail particles, and then compare the simulated visualization with the actual photographic observation, which was done then in October 2014 by the Mars rovers existing on the surface, Opportunity and Curiosity, and then adjust the simulation parameters to match those visual observations to make sure that the simulation provided a realistic model of what was actually happening, and then check out what parameters of the individual tails are needed to provide first the visual appearance, and then secondary, is it possible with these parameters to achieve this high mass transfer to the orbit? FreeFlyer offered here the interesting aspect compared to other software that I could interactively work in the simulation with a really quick iteration time of a few minutes to adjust my simulation, and with the visual appearance verify that it was actually realistic. And I created the first variation of this, a few hundred lines of script code, already 2 years ago. And that already achieved a visual match to the observations, but had some limitations I explained here. And technically, I used the formation of spacecraft objects, and each spacecraft object was just more a dummy object to gather data and be influenced under gravity and the solar pressure. I didn't add any other propulsion effects to it except for the initial ejection from the comet surface. But in the first variation, it turned out it was insufficient and I needed to add some artificial force even, but that I could later revalidate and change. And to give a bit more overview about the context here, the used parameters for the individual particles are governed by the two forces, and in cometary science, the relation between those two forces, radiation force and the gravity, is called the beta factor. And this is in describing the characteristics of individual particles, because the beta factor is in the end only depending on the density of the particle and its diameter or size, not the distance, because both forces are inverse square law following. So it's interestingly, it's a constant factor, at least in the range of planetary solar system. The complication I saw at first, you need to take care with all those high magnitudes of parameter differences to use the correct scaling factors between the different units, and to find a balance between the simulated particle quantity. I used 1000 to 3000 here, and acceptable iteration frequency so that I can revalidate the model, run it again quickly. But in the end, the first simple variant provided already a good visual match. As you can see here in the center, this opportunity ROA photo, the second from the left, is actually the surface observation. And you can see the comet here as a really dark spot blob here between three background stars, Alpha Piscis, Alpha Ceti, and Mira here. And the simulation showed the comet at exact the same position from the surface seen from the opportunity location on Mars as it was in reality here. Interestingly, I could see that a few hours after the close encounter, it disappeared into daylight here. I could simulate the daylight also on the surface, as you can see in the brighter sky. And on the left side, that is a different hypothetical observation location, site C here on the Mars surface, where it would have been a much better site, as you can see here. 2 hours, or during that time here is a close encounter time. And at that time, it would have been visible in the night sky here at the site C hypothetical site. But even with this good visual match, I had the problem that I needed to introduce an artificial force, anti-orbital velocity. And finally, only a few days ago, I revalidated it and tried to introduce realistic parameters without needing this artificial force. And I could achieve it within with only 3 days now. This is the result on this second variation. And you can see it really looks like a comet with a bent dust tail bending following the orbital velocity. And you could imagine here, not directly visible here, that the ion tail would go straight then. That is here in this reduced particle amount simulation, not possible to, at least in the quick variant here, that I introduce many different particle densities. And at first I hesitated to use this variation too, because I considered it would require too long simulation times, but it turned out with those 1,000 particles, I needed to run the simulation at the starting epoch 1.5 years before the encounter in January 2013. But the runtime is only half an hour then, because I could reduce the gravity forces to the sun and the comet then. I verified it a bit, comparing the differences, and the difference was only a few thousand kilometers near Mars then, so that I could then simplify with reducing to two objects influencing the gravity. Some more visualizations from this realistic particle simulation. The surface view also shows the classic comet shape. It's a bit brighter than the actual photos, but you could imagine if it's a longer exposure time, then here's a 30-second on the surface Opportunity rover camera. It would have provided a bit brighter imaging. And even the direct comparison, it's not that much different. As you can see here in the screenshot, that is a surface view from the ground station that is in the same magnitude, I would say, of the brightness. The shape also interesting, classic comet shape. Here in the solar system view. Here in this run, the visible tail length is too long here for this small comet that is about 3 million kilometers. But those far away regarding distance from the nucleus tail particles are not really visible because the density is too low of the cloud here. So what you see here is most likely a range of maybe 5,000 to 10,000 kilometer tail lengths here in the surface ground station views. Findings, good result that I could visually simulate a comet tail with FreeFlyer. That was a good first result. And it produced the realistic tail behavior shape with the natural parameters. I could see that a trajectory exists which reaches Mars from the nucleus if you start early enough. That I can later show when I go directly into the simulation. Here you see a bit roughly overview that the distance between nucleus and Mars is about, here at that time it's 300,000 kilometers. And you could imagine that some of the particles could reach the planet here. We at least see already some in the range of 10,000 to 20,000 kilometer distance from the surface. And I imagine if I increase the density, the quantity of the particles, that I would see some of them reaching in the range of less than 5,000 kilometers, or in the range where it could impact the upper atmosphere. But that would, with a FreeFlyer version, would then increase the simulation time to several hours. But I will try that later. So the trajectory that could be achieved with realistic parameters. The question is, would be the high mass flow also achievable? Currently, it doesn't look like that because with the realistic parameters, it would mean an ejection rate of a few hundred kilograms per second from the comet, and with that, you cannot achieve, at least with isotropically ejection simulation, this high density to achieve 80 tons in the intersection of the planetary surface with a huge comet tail. So you would need 10,000-fold the amount of 100 kilograms per second with the isotropically ejection model. And with that high rate, you would deplete the cometary matter of the nucleus within 1 year or less, even half a year, maybe even. So that is still an interesting question to solve to achieve this high rate of mass transfer. Maybe a solution is to introduce other forces, like the well-known electromagnetic forces, which are actually much stronger in relation to gravity. And that might be an interesting option then, especially with observation of comets which have been made of their plasma environment. And it looks like the ice ball comet model is really challenged there. In the future, this same script could be used to simulate meteor streams. Those are actually also related to comets because they are the remains or they are particles highly focused on the comet orbit. They stay there in the orbit as a trail for up to many decades, which is also difficult to explain why they are resisting the solar pressure there with being quite small particles. That could be also investigated with a really similar script in here. The impact of FreeFlyer, as I said already, the realistic visual simulation, the interactive ability to quickly rerun with an iteration frequency of a duration of only a few minutes each iteration that allows them to quickly adjust and develop the model. Previously, scientific papers who wrote about predictions in the year 2014 and then one later about observation. The prediction analysis used also, of course, simulations, but you cannot find any three-dimensional interactive or visualization in 3D, in public at least. There's one on the cometcampaign.org website here, but that is really simplified, abstract, only really is a 3D view, but a really simplified, not naturalistic view, which doesn't provide the complete context that it can even directly visually validate the model. What I could see that the existing FreeFlyer functions allowed a quick build-up of the model. Within a few minutes, I could see the initial results already, and then over a few hours, refine it and then achieve the variant first I explained before. And then the second variant needed additional a few days only to have the realistic particles inside it. The scientific result was the mystery is confirmed. At least with existing forces here, but it can be used to investigate further here. New insight, interestingly, with the ground station views, I could see the view there against the background stars. You could see what is the radiant point where was the comet visually coming from compared to bright background stars and where it is disappearing into. And I can reuse the implementation later then for similar problems like the comet trails resulting in meteor streams, which is especially now with improved infrared observation capabilities also interesting because those meteor stream comet trails are only visible in mid-infrared, and it has been already seen for 70 periodic comets in infrared. Lessons learned, best practices, reduce the gravity object simulation to speed up it if you can within the constraints of the accuracy of the model. Let's here see limits the particle forces to the solar gravity and the comet gravity itself. Add report table views to verify your model and provide internal parameters to quickly adjust it if you see that they are run out of the constraints. A simple add a field of view of 53 degrees, because then you can use the field of view as a simple scale, because the scale of the width is then the same as the distance, which is displayed in the FreeFlyer view. The support was a great help. already 2 years ago for creating the first variant, like a suggestion to use a dummy spacecraft to get more data, which are not available for celestial objects there. I could see it was only, unfortunately, running single-threaded in this version I have, but I heard there's another one which can run multi-core systems and utilize them better, so I could speed up the iteration frequency even. And I could use the classic the provided functions like the sensor cones. Here I use them as visibility range from the ground rover views. And let's take a look at the simulation itself here. I have run it already earlier today, so I can quickly iterate through it here. Here, starting in early 2014. On the left, you have the ground track view with the ground stations, hypothetically site C at 40 degrees north, solar system view, the Mars view here. And the in-space comet tail view. The particles are already ejected here during this time. Total amount is 2000 here, ejection rate. The beta parameters quite low here, because in this, this is a variant 2 with the realistic parameters. I saw that at least here for my low number of quantity, I need to increase the density of the individual particles to 7 gram per centimeters cube. That is density of iron. Because if I use density of, at least in my simulation, of only 1 to 1 or 2, the solar pressure force was much too high, and they disappeared then quickly and could not reach near the planetary atmosphere. Here I use a step size of 1 day, and that step size is quickly reduced now to 1 hour. In a few seconds, the October 10 we are here, and you can see the tail appearance from the ground views here, developing. I added 3 background stars here to register with the actual photographic observation from the Opportunity Mars rover. Opportunity Mars rover is the center image here. And now the October 19, the day of the close encounter, 6 hours before. And it's really nice to see the spatial view here. You get the perspective effect that the tail is actually here flying over you, being on the planet. You can see the perspective effect. That is a big advantage of this interactive view, 3D view. And you could imagine that here, when the tail plane is intersecting with the planet, that some of the particles actually reach the upper atmosphere here, better visible in the space-based view here. That is a close encounter, and we need to go 2 hours to the future here to get the intersection of the tail plane with the planet. Here's the planet. And here you can see the tail plane is intersecting with the planet. And some of the particles are in the vicinity of the planet here, we see here. Internally, I outputted also a list of of the nearest particles, so I can have a table and actually see there the result of the few particles reaching near the impact location. The solar system view. There's a path trajectory. Here the tail is a bit too long compared to realistic visualization. It's about 3 million kilometers here. I use a small trick to recycle the particles, so because I need to be limited to 1,000 particles to achieve a quick iteration duration here of only. This was running half an hour, the simulation. So particles which reach a certain. If I run out of my particle space of 1,000, then I just remove the furthest particle with the largest distance and just remove it and create it new then as newly ejected particle.
This is amazing, Holger. We are out of time.
Yeah, I'm also good now.
Can you flip back to your slides? You have any contact information to share?
Yeah. I'm on Twitter or on my website with all the contact information, or also via email if you like.